All right. When we deal with 2, 6, and 2, 7, that's the only thing we have left. The reason why we split this apart from with 2, 6, and 2, 7 away from everything with 2, 1 to 2, 5 instead of just having, it's just two sections, but at the same time, 2, 6, and 2, 7 are completely different from where we were just at. Before, with 2, 1 to 2, 5, everything dealt with polynomials, quadratics, cubes, fourth powers, things like that. Everything was nice and neat and had smooth curves. It had no restrictions. With a rational function, however, this is where you are going to have restrictions. This is a lot like what we did in the P chapters where we factored everything out. We talked about the denominator and what it can't be, and then we factored it and we solved and everything there and simplified. Here what we're going to do is we're going to take those same rational functions and we're going to graph them. Okay? So a lot of what we do we've already done to a certain extent, but now we're going to put them in a graph and kind of go from there and figure out what can all of my x values be for, and what is this going to look like. Okay? So whenever we talk about the domain, remember the domain only affects the denominator of our rational function. Okay? In terms of what we look at as far as what our domain can and can't be, and if there are restrictions, okay, before whenever we dealt with the polynomials there were no restrictions. It just went from negative infinity to positive infinity. It's not that simple anymore. Okay, so realistically, all we have to do to find the restrictions as far as what x can't be is to just set the denominator equal to 0. Okay, or I guess in certain x minus 5, I guess it's actually not equal to 0. Okay, it's the 1 or 2 values, or maybe 3, depending on what you have, as far as what x can't be. Okay, so like in this case, the one value that x cannot be is going to be positive 5. So if we would actually write the domain of this, okay, remember, before with a polynomial, it went from negative infinity to positive infinity. You're still going to have the same domain. You're still going to start with negative infinity. You're still going to end with positive infinity, but you're going to have gaps. Okay, you're going to have small little windows that your domain is going to kind of jump over. So if we if we only have one restriction, then our domain is just going to go from negative infinity to 5, and then it's going to jump over 5 essentially, and then go from 5 to positive infinity. I'm going to go back and forth with the graphing calculator so you can kind of see what it's talking about, okay, in terms of how the restrictions work. Okay, so if I have x squared minus 25 divided by x minus 5, and if I put this in a graphing calculator, okay, and we actually graph it, okay, I'll be the first to tell you your calculator is going to tell you a lot of the story as far as your graph is concerned. Okay, so if I had x squared, was it minus 25, I believe, okay, divided by x minus 5. Now, if you're going to use your graphing calculator and you're going to put it in here, make sure you put the parentheses around whatever's on top over whatever's on bottom. Okay, because if you don't, then you can get some really screwed up answers and it's going to think that you are having x squared minus 25 divided by x minus 5. Okay, if you just try to type everything straight in. So whatever you have on top, put it and group it in its own parentheses. Whatever you have on bottom, group it in its own. Okay, whenever you go into that y equals window, so then you can kind of see what's going to happen. So as we go here, what happened? Oh, because it divided. If we plug that in, what do you notice as far as my table's concerned? There's an error at 5, right? Okay. So in this case, because we had x squared minus 25 divided by x minus 5. Okay. The x squared minus 25 can factor out, right? Okay, bless you. So it can factor. So in this case, this is what's called a hole. Okay, so it's just going to be a continuous line because whenever we simplify everything, okay, there's just that one spot. Okay, and then our graph is just going to keep moving on. Okay, but it can't be 5 because of that restriction. Okay, it's not as simple as, hey, it can go from negative infinity to positive infinity. Okay, but because of that 5, because where we started, and whenever we divided by x minus 5, okay, it's going to give us that error. Anytime you have an error, that is your restriction. Okay, or whenever we get into it, that's going to be what's called, most likely going to be a vertical asymptote. Okay, which is just an imaginary line through that point. Okay, in this case, it's really just a hole because that's the only spot that x. Same way then on 2 is if I have x divided by x squared minus 25. So if we have restrictions here, x squared minus 25 cannot be equal to 0. So x squared can't be equal to 25. So then what can x not be equal to? Plus or minus 5. Okay, so then for my domain, again, it always starts at negative infinity. Where's it going to go to? From negative infinity to where? Negative 5. Then from negative 5 to positive 5. And then from 5 to positive infinity. Now, whenever I say that it goes from negative infinity to negative 5 and then from negative 5 to 5, is it really going to be on negative? What's the only thing keeping it from being at negative 5 and positive 5? Like that parenthesis just means that it goes all the way up to it, right? And then we're just jumping over it and then we keep going and we go from there. So this one's going to be a little bit better as far as how we see it. So if I have x divided by x squared so what do I have? X on top divided by x squared minus 25. So we have basically our windows. Okay, if we go into our graph, okay, or go into our table, excuse me, and kind of look at everything. Okay, you have an error at the positive 5. We go up to negative 5, we have another error. Okay, your x value can't be where there is an error. Okay, in terms of our graph and what we're going to talk about here in just a second, is that, well, we'll just go ahead and talk about it now. Basically, you have what's called vertical asymptotes. Vertical asymptotes are kind of like imaginary lines, or they are imaginary lines, that your graph cannot go through. Okay, it's like a force field. Okay, you can go up to it, but you never can get all the way through it. You can see to the other side, but you can't get through there. Okay, something else has to start. Okay, it's not like a wall. Okay, you can go through a wall. Okay, you can't go through a force field. Okay, not until their shields are down. Okay, you can go up to it. You can see everything inside of it, but you can't get past it. Okay. Now, with a graphing calculator, I will tell you that it's not one of those things like with the blue lines. Okay, and it's hard to get students to understand that basically what happens is that as I draw this, and you can only see what you can see, but if you do have a graphing calculator and you take that blue line on the inside is just continuing to get closer and closer and closer to it. Same way, it's getting closer and closer and closer to it as it moves down. It continues to go off in a positive or a negative direction depending on where it's going. Okay? Your graphing calculator, you're not going to be able to see it. Okay? You're only going to be able to draw it physically with a pencil. Okay? You can only get as close as basically that pencil lead or whatever you write on your paper, right? Okay? So it gets closer and closer without touching it as it keeps moving on. Okay? It's basically going to get all the way up to, in this case, -5 on the left and the right side. And the same thing as far as the +5 is concerned. Okay? It's going to get as close to it and kind of just squeeze everything to it as best as it can, or as close as it can. Okay? But you're not going to see that as far as in a standard -10 to +10 window. Are there any restrictions on 3? Or what are your restrictions? What can x not be? If we set x squared plus 25 equal to 0, or not equal to 0, however you want to look at it, what can x not be? Is it plus or minus 5? Huh? Plus or minus 5? What? Well, it's x squared plus 25, right? So x squared plus 25 can't be 0. So that means that x squared can't be equal to -25. Means if we take the square root, x can't be equal to what? What's the square root of -25? Huh? Plus or minus 5i, right? So then, where's 5i on a real number line? Where's an imaginary number on a real number line? Nowhere? Above it? Above what? Okay. On the graph. It's imaginary now. Can you see your imaginary friends?
Yes.
Can your friends see your imaginary friends? No? So are your imaginary friends real? I didn't ask that question. Huh? So if you get an imaginary answer here, are you going to have a restriction? No. Is there any time that is going to be 0? That x squared plus 25, is there any number that I can plug in, no matter how big or how small? What if I plug in a negative number? What if I plug in a -5? What's -5 squared? What's -5 times -5? 25, right? Well, what's 25 plus 25? 50. So that didn't work. Okay? What if I go really, really small and I go like negative and I do like maybe like a 1/2 or even just a regular 1/2? What's 1/2 times 1/2? 1/4. Still positive. Can I ever square anything and get a negative answer? No. Okay? So since it's that plus, there's no restrictions on here. So my domain is just going to be -infinity to +infinity. There's no restrictions that I have because I end up, whenever I solve for the x squared plus 25 and I solve for my x, if you end up with an imaginary answer in your denominator spot, or as far as what x can't be, if it can't be imaginary, that means that it can always be real. So you have vertical asymptotes and then you can have horizontal asymptotes. Okay, it's real simple. Vertical asymptotes talk about moving from left to right as far as on your graph and what x can't be. Those are your restrictions. So if you have any sort of restriction, okay, from the denominator, that's going to be your vertical asymptote. Okay? That's the value that can't be x. Whenever we talk about our horizontal asymptotes, okay, locating the vertical asymptotes are real simple. Set the bottom equal to 0 and solve. Those are going to be where your vertical asymptotes are. Okay? It's basically what it says here in this note, okay, that a value where the denominator is 0 does not necessarily result in a vertical asymptote. Okay? That's kind of like where we had that hole. Okay? But it will give you your restrictions, but it'll have to be a certain time whenever it'll be a vertical asymptote. Okay? But know that there are kind of those imaginary lines and things like that, but it will give you a restriction. Your horizontal asymptotes are just basically, it is what it is. It's a horizontal imaginary line that your graph will get closer to. Depending on what you have, sometimes you may have holes, you may not have holes, you may have vertical asymptotes, you may not. Okay? Your asymptote in your graph can run, basically it's just running to that, it's like running to that magnet. Okay? Either from the top side or the bottom side of it. Now, whenever we find asymptotes, and I think it's going to be easier if we just show you basically on a graph, if we have 3x minus 3 over x minus 2, okay, if I would graph this, and I have 3x minus 3 divided by, what was it, x minus 2? This is what my graph would look like. Okay? It has horizontal and vertical asymptotes. If it was 3x, okay, if my function was 3x minus 3 divided by x minus 2, where's my vertical asymptote at? What is the one value that x cannot be? Positive 2, right? So, how did you get the vertical asymptote? What'd you do? It couldn't be, the vertical asymptote was at x equal to 2. Just took that, set it equal to 0. Shut up. So I've got an imaginary line, kind of, going through 2. It's getting closer and closer to that red line. Now, I also have a horizontal asymptote. Okay? Horizontal asymptotes are really simple. Okay? All you have to do is pay attention. Look at the powers of the lead coefficient on the top and the bottom. Okay? So if I have, and it says in the notes, if I have like a to the m power over b to the n power, it's real simple. Okay? This is for my horizontal asymptote. You have to figure out, is the power on top bigger, the same, or smaller? Okay? If they're the same, okay, because if I have 3x over x, are they the same power, or are they different powers? They're the same powers. Okay? If they're the same, all I'm going to do is take A divided by B. What's A in this case? 3. What's B in this case? 1. So, what's 3 divided by 1? 3. So, I have a horizontal asymptote here at 3. Okay. Both graphs are getting closer to that y equal to 3. Oh, hold on. I wrote that backwards. Sorry. It needs to be ax to the m power and bx to the n power. My fault. So I take whatever that lead coefficient is out in front. If they're the same, I just take whatever's on top, divide it by whatever's on the bottom. Now, we'll get into the graphing side of it, but that is basically how you're going to find your asymptotes. If I look at the next one on 11, and we'll just keep going, we'll kind of take the next step tomorrow with the other ones. If I would graph 11, and I have y equals, I have 2x squared divided by, those are the same. I don't like that one. If you printed it off and you have x to the 4th. Divided by x squared plus 2. What do you notice? Do you have a vertical asymptote? Do you have anything that the x value can't be? If you have x to the 4th, you have x to the 4th over x squared plus 2. Is there anything that x can't be? No, there are no restrictions, right? Now, do you have a horizontal asymptote? Is there something that it's getting closer to? Okay, we said basically you had to look at the 4 and the 2. So is the power bigger on top or smaller? It's bigger. Okay? An asymptote means that the line is getting closer and closer and closer to it. Is the line, or is my graph, getting closer and closer to a line? Okay? Is it running to something that is horizontal? Or is it just kind of have a minimum value? It just has a minimum value, right? So if we look at ax to the m power over bx to the n power, if m is greater than n, there is no horizontal asymptote. So when they were the same, we just took whatever the lead coefficient on the top was divided by whatever the lead coefficient on the bottom was. Now, if m is bigger than, or if my power on the top is bigger than the power on the bottom, there's not going to be a horizontal asymptote. So if we just flip the x squared and the x to the 4th, to where the last type is when they are whenever the top's smaller than the bottom. What do you think is going to happen? Like in this case, what do you think my asymptotes are going to be? First off, what's the vertical asymptote? 0. Okay. So vertical asymptote is at 0. Okay. It's getting closer and closer to it as we move. What's my horizontal asymptote? Where's my line going? Where's it getting closer to? 0. So the last thing, as far as the horizontal asymptote, if I have a m to the x power, I'm sorry, backwards, a x to the m power over bx to the n power. If m is less than n, y equals 0 is your horizontal asymptote. So if that power on top is smaller than the power that's on bottom, it is automatically going to be a horizontal asymptote at y equal to 0. Vertical, real simple. Set the numerator equal to 0. Horizontal, you have to look at your powers of your lead or of your highest degree on the top and on the bottom. Everything's in Canvas.